Welcome to session 25 on beams. In this session, we're going to have the opportunity to discuss the deflection of beams and the forces associated with these deflections and moments associated with these deflections from a slightly different perspective than what we did last time in session 24. We're going to come back to superposition, which we used with axially loaded systems, and breaking a system apart into different subsystems that we can then solve and add or superpose together, as you see here and as you see here. In the next part, we'll discuss indeterminacy. So indeterminacy is when you have more reaction supports, as you see here, than would be necessary to solve the problem. So you actually end up with extra unknowns and not enough equations just through equilibrium to be able to figure out what the supporting forces or loads or reactions, whether they be moments or forces, might be in the system. Okay, so even for example over here you have a reaction moment and you actually have a couple axial loads, one horizontally and one vertically. Anyway, and then in the final portion, we'll get into thinking about beams as springs, which again is a concept that should be familiar because we've done this with axial systems many sessions ago. So in sessions 3 and 16, we discussed superposition. And we said that it's the net response caused by two or more stimuli. And you can think of it as a sum of responses. Right? So maybe a more basic example is to think, well, I've got one force being applied to this bar, and if I apply another force to this bar, and it has a second displacement associated with that second force, just as there was a displacement associated with the first force, I can add these displacements to each other and understand what the contribution of these combined forces might be. It's similar with beams, but a little bit more complicated, okay? Because this type of problem is kind of 2.5D. What are we talking about? So we're saying again that this superposition is applicable to linear systems, and the portion that's maybe a little bit more complicated is that not only are we looking at how the individual loads lead to displacements, but we also want to keep in mind that there could be issues with slopes. And in fact, we kind of looked at this very early on when we had beams and some rigid horizontal members that were connecting these bars. Did I say beams? I said when we had bars and we had rigid beams connecting them, and there was some rotation if you go back and look at what we did a while ago. So we have encountered this idea of having to not only deal with the displacements, but the slopes, and this will be another example. So the approach is essentially to make sure that we sum these individual displacements, and we also account for slopes from the individual loads when we're calculating this overall displacement. So as kind of a system that we might look at, and in the next slide we'll get into more detail on this, we have a cantilevered beam. It has two loads, okay, one in the middle and one at the end, and we might be looking at the overall displacement at the right end. We can break this down into being a system that has the load from P, and that's applied in the middle, and then say, okay, there's some delta P from this applied load here, and as you're probably thinking, now I've got to have this other load Q, and so I'm going to put that here, and I'll have on the right this delta Q, and we'll say that the overall deflection can be thought of as being delta P plus delta Q. Okay, now let's go into more detail because this is truth. Okay, what we're seeing there, but it may be a little bit more complicated as we see when we, especially on this step, when we're trying to figure out delta P. Okay, and if you have a table that has, I guess, this exact configuration, then it's not a big deal, okay? But what if we only have this information. Okay, when I say this, I mean, what if you only have, and I don't have the diagram here, but we only have the relationships for displacement for a cantilevered beam, okay, essentially this system right here, a cantilevered beam with a load at the end, and we have displacement, okay? So that's what this pair of equations is describing. It's describing what is the displacement as a function of x if we're moving along here, and it's describing what is the maximum deflection, which happens at the end, okay, from this applied load Q. In this case, you know, it's written P here, but we know how to substitute. And this W is what we usually call V. All right, so coming over to writing the equation that's here in a little bit bigger view and in our terminology with V, it's the convention is maybe a little bit different, okay, because often we say it's negative, right, when we've been integrating, because we say, okay, we're going to find V in the vertical direction, positive, upward, okay, but here we're going to use a little bit of our experience and understand that, okay, this V is actually, the displacement's going to be downward, okay, with these loads. So this is just writing that expression for displacement across. It would be essentially, well, this is Q, but this is P, all right? But if you had a P here, it would be the displacement across this cantilevered member. And the slope can be calculated across here. They didn't give it to us, or I didn't give it to us, by taking the derivative of V with respect to X. Okay, so if we do that, this is the expression that we have, all right? And so if we're interested in the slope at the end of the member, we can plug in L, and that gives us the slope. All right, so if you're just given this displacement, you can calculate out the slope. Make sure, though, you don't substitute in L first, okay, and then you can't take the derivative with respect to X if there's no X in the equation, right? So you got to do that with the equation that's a function of X. So now, what are we going to do to represent this system, okay, in this form with these equations that we have? And this is where we want to keep in mind the slope. And you know, I'll say there are table values, okay, that have exactly this configuration. So you don't have to do all this work, all right? But we're trying to show how you can use this configuration to figure out what the displacement is here when the load is applied in the middle. And so the basic idea is we're going to pretend that this load P is acting at the end of a cantilevered beam. All right, okay, fine. Because all this material right here is not experiencing any internal shear or any internal moment. Nothing is happening in this. This is essentially acting as a rigid member, okay? It's along for the ride. But unlike some of the problems that we've discussed, like with axial loading, when you have a region that's got no internal force, normal or axial force in it, and it's along for the ride, you know, it just shifts to the right, shifts to the left, or, you know, goes up or goes down, right? We still have, at this location, we still have a slope, okay? So if we model this as being at the end of a cantilever beam, that's fine. Delta 1 is going to follow this equation, or actually this equation, okay, at this point, but we have not a length of L, but a length of L over 2, okay, that's fine. But if we're interested in what is happening at delta P over here, okay, then we've got to also account for the fact that it doesn't just, it's not the same position as delta 1, okay? Like, it's because it's sloped, right? So it's going to go down. So even though there's nothing happening over here, it's going down, all right? So what we want to do is we want to find the slope there, and then if we know the slope and we know the length of that portion, which is L over 2, we can calculate out what the additional displacement would be and write that out, okay? So we want to know the displacement and we want to know the slope, theta, where, quote, L now for this equation or this equation or this equation is not the L, but it's L over 2. Okay, because what we're saying is now the entire length of the member is L over 2. So we can calculate that out, right? We can say that delta 1, all right, just right here, is just taking this and substituting L over 2. So we get L over 2 quantity cubed. And so we now know that delta 1 is PL cubed over 24 EI. Whereas before, and then as you'll see when we do this member, it would have just been the QL cubed over 3 EI. Okay, or this equation that you have right here. So what do we also think about? We also think about the slope. So again, we're going to plug in L over 2 into this equation up here, and we're going to say, okay, well, it was L squared, now it's quantity L over 2 squared, so that's going to be L squared over 4, 2EI, and we get an expression for the slope. Now, we want to get delta P. I know what this displacement is. I know what this slope is. I know what this hypotenuse, I could call it if I want, right, of the triangle that's describing going down. So if I know this is a hypotenuse and I want to figure out the opposite, then it's L over 2 times sine of theta 1, okay, of this quantity. So that's what we write out. Delta P, the overall delta P here, is going to be the delta 1 that we calculated here, plus L over 2 sine of the angle, all right, that slope. Now, what is delta Q? Delta Q is just what you have here, substituting in Q. So QL cubed over 3EI, very straightforward. So the overall delta is this delta Q plus delta P, or this delta P plus this delta Q. So here we go. We can write out this large expression. Now, you're thinking, well, I haven't really seen many of these table values that have a sign in there. And you'd be right. That's odd. And you might also be recalling that we said that we're going to have small displacements and small angles when we're doing Euler-Bernoulli beam bending. So we can assume that this angle is small, which means that the sine of this thing is approximately just this thing. And when we do that, we get L over 2 times PL squared over 8EI. Okay, so that comes out to PL cubed over 16EI. And look, we have 1/16 plus 1/24. That is going to be 5/48. And so we get the overall displacement is 5 PL cubed over 48EI plus QL cubed over 3EI. All right. And it turns out if you look at some tables for this particular configuration, this is what you have. Okay, and so we did in fact do this at least correctly according to the tables that we see and according to the reason that we've shown here. So this is an example of taking into account the angle, the slope, right, the angular slope, along with displacements to be able to calculate the overall displacement of interest. Let's do another example, and I think this one's actually kind of simpler. It is simpler than what we just did. Here we have a configuration with a pin-pin beam with 2 loads applied. And we have in the past had tables giving us, or values in tables or schematics in tables that have given us the resulting displacement when you have a load across a pin-pin beam and you're interested in figuring out displacement at some location across the beam. So in this case, we're interested in the overall delta, and it's going to be equal to delta 1 plus delta 2, and delta 1 is a result of the load P, and delta 2 is a result of the load Q. Maybe we could have said delta P and delta Q instead, but anyway, I put in delta 1 and delta 2. So here is one of those tabular values for geometry. Okay, here they show that A is equal to 0.8 L, but really that's what they're showing here, but it's really a general expression over here, okay, for if I have some A and I have some B, okay, and A plus B is going to equal the overall L. And we have expressions so we can figure out displacement at a given location, right? And once again, we want to just be aware that we often state V is positive in the upward y direction, so that these would be going negative. And in our case, we're going to say that we have A equals L over 4 and B is equal to 3L over 4. And which one am I referring to in that? I'm saying this case right here. So now for delta 1, we can write out this expression that we have right here. Sorry, it's this one. Or, yeah, either, I guess, whoops, either, sorry, I got to be careful. We're interested in the delta 1 beyond, right? So A is going from, it's just L over 4, but we're actually interested in delta 1, right? So we're at L over 2. So that would qualify our X is at L over 2. Our load is at A. Okay, and so that's why we write out this equation that we have here, the second one. So now we can do a little bit of substitution, a little bit of simplification, and a little bit of algebra to get this expression. And we can use this expression right here. This is a more standard one, which we also have in session 24, or you could just plug in A equals L over 2 and get it, but this is a more common expression that you'll see. And so what are we saying? We're saying that, okay, I have a delta 1 here, I have a delta 2 here. I don't even have to worry about the angles, okay? Because what's nice is that this expression describes displacement exactly at this point. I had to worry about slope when I was projecting to a location that was not exactly described by the equation I was using or the configuration that I was using. So here, delta 1, delta 2, add them to each other, and this is what you get. Okay. It's question time. So here we have the following configuration for a beam, all right, and a couple of helpers, okay, in terms of how to go about doing this. And the opportunity here is to use these expressions to and use superposition to be able to figure out what the displacement at the end of the overhang might be. And just it may be a little subtle, but to keep in mind that at this location, all right, so if there was no overhang, you have P acting in the middle, so this looks like a pretty nice approach to use, okay? All right, but we're interested in what's happening over here. So what we need to do is we need to figure out, we know the displacement here is going to be 0, okay? That's fine, okay? But there's going to be some slope, right? This is going to sag down, and so there's going to be some slope. So what we need to do is we need to figure out what the slope is here. It's going to be coming off. It's going to be coming off kind of with a positive angle here, all right? And with that positive angle, okay, now the question is, what do you treat this member as? Well, you say, okay, it has a slope, so if it were a rigid member, then I could project up to where it's going. But it's not a rigid member, okay, from here to here. It's essentially a cantilever member because there's material here, okay? So this is like, you figure out what the slope is, and then you've got a cantilever that's projected out, but it's also bending down, okay? So I don't know if I can, kind of like that. So what's going to happen is the displacement won't be as far down because it's been, so if I just look at, okay, plug in Q here, all right, and figure out what the displacement is, all right, I'll get a value essentially based on this equation right here. but that member has been tilted a little bit with a slope, so it won't be as low. So that's what we have to account for here. So essentially, it's a superposition with three things. It's got this portion here to tell you, okay, what is the slope there? Then it's got a kind of rigid approximation of that slope for how high it would get, and then it has this: how much is that region going to droop over as a cantilever? All right, so it's a problem that you get to approach, and I'll see you in the next portion of our session. Thank you.